Hello and welcome to our next discussion on statistical significance. The first term that I want to introduce is that of effect size. Essentially, we are trying to just classify the I guess the word is significance, the strength of our sample information, the evidence that we collect in our hypothesis testing procedure. So if we refer back to our personality rating of physical attractiveness example, where we try to investigate if the rating improves from the average of 200 based on the sample provided and the evidence collected. And we got a sample mean of 220. If we then overlay the distributions for population 2, sort of the reference population in our null hypothesis, and the population 1 suggested by way of this sample, if our sample is a good representation of the true mean of this new population 1, then you see that it's in truth this dotted line over here, and the effect size essentially measures the gap there, how far away population 1 actually is from 2. The effect size would be different if my sample mean was not as far away as before. Now, of course, we have to standardize this to not have the actual size of the raw scores in place so that we can compare them. So the effect size formula is going to be D, which measures the distance between the two means, the reference one and the sample mean, which is taken as our best guess of the population mean and divided by the standard deviation to standardize it in a sense, right? This is also called Cohen's D, the effect size, to measure the strength of the evidence that we collected by way of the sample. Let's try to scroll down here, but my laptop is a little slow today. Come on. We can do it. There we go. So I'll squeeze it in here at the bottom to not reveal too much. What is the effect size for this example? Well, our sort of reference population mean is 200. We got a sample, let's say, of 208, standard deviation of 48. Then we calculate the Cohen's D, the effect size, and we get 0.17. If, for example, we do the same thing, but the difference between the population mean and what we measure is 16 instead of the 8 here, then you see the effect size increases because the gap here is bigger between those two examples. If, however, we go back to the 8, getting us this effect size of 0.17, but we have a smaller standard deviation, you see then the effect size also increases because you have less variance in the population in the distribution so that even a small shift is more significant compared to a larger variance in standard deviation. All right, so effect size is one measure of the strength of the evidence, so to speak. So we can classify them to keep it simple. Zoom in a little here. Small, medium, and large effect size. Small being around 0.2, medium classified around 0.5, and large around 0.8. Now, these cutoffs are somewhat arbitrary, but it's just to refer to effect size in a more convenient way. Let's see if that was this tab, right? This one is next. Okay. So let's make this as big as possible. Let's a little too big. Okay. Zoom out, laptop. Laptop says it'll zoom when it feels ready to zoom. But we can see. If we, now I zoom too much. This is one of those days. One of those days that I'm asking too much of poor laptop. That's okay. We'll get through it. If we think about the hypothesis testing results, 4 things can happen. If the null hypothesis is true, in fact, and for example, there isn't a significant change in treatment or anything from the baseline population, but we do reject it. Our sample is extreme enough to reject it. That is a mistake. We'll call that a type 1 error. And we've seen before alpha is the probability then of being in that extreme cutoff region. Alpha will be the probability of making a type 1 error. Of course, if the null hypothesis is true and I'm not in that extreme case by way of my sample, we do not reject the null hypothesis and that decision is correct. Let's make my cursor a little smaller. If the research hypothesis is actually true, meaning the null hypothesis is not true, we should reject it. And then getting an extreme enough sample, making the conclusion to reject the null hypothesis is the correct decision. However, the research hypothesis is true. The null hypothesis may in fact be false. We should reject it. However, we might not. If we base it on our sample, and our sample is just not putting us in a position where we do not reject the null hypothesis when we in fact should. So let's talk about this, what we call the type 2 error. So type 1 error is I reject the null hypothesis, but I shouldn't have. A type 2 error is I do not reject the null hypothesis when I should have. So let's explore this by way of an example. But first, we will actually, I'm going to refer back to this in a second. Let's start with our example. Let's go with one of the examples that were discussed previously, personality attractiveness example, where if you we were trying to investigate if the attractiveness, let me just remember what that was. Was it the personality rating based on attractiveness? Or it doesn't actually matter, right? we have our baseline population of 200, and we're trying to see if the rating increases by way of this extra information provided to the people in the survey. And what we got was our sample mean here. What should we call it? I should just make my cursor even smaller, apparently. Sample mean, which we get as 208. And then we see, well, is this significant enough to reject the null hypothesis? Is this far enough away? And so on. So if we visualize this, once the page wants to transition, we have our 200 in our comparison distribution. We have an alpha of 5%. That's what we're okay with to decide if we should reject the null hypothesis when the evidence is strong enough that if I get something out here, that's pretty unlikely. I'm going to see that as evidence that the mean is in fact not 200, but a change has occurred. So when I look up my table, I get a z-score. Now my cursor is too small. Z-score of 1.64, that corresponds with a 5% alpha. If I then see what is the raw score that corresponds to that, I see that is 209.84. So now if I look at the raw scores instead, let's think about this. This means that if I get a sample mean from my investigation of more than this, I will reject the null hypothesis and view it as strong enough evidence that a change has occurred. So we get our cutoff raw score of 209.84. Now, in this discussion of a type 2 error, remember, the research hypothesis is actually true. So we should reject the null hypothesis. The null hypothesis is not true anymore. So, of course, our best guess for the true position of the distribution is centered here at our sample mean of 208. So if this is actually the case, research hypothesis true, then we're actually looking at this distribution up at the top. And if I follow this 209.84, scroll down, laptop, come on. There we go, thank you. 0.8. I'm trying to write. Come on, laptop, you can do it. I need you. 84. Just can't do anything too fast. The laptop needs time to think. Then I am going to reject the null hypothesis in favor for the research hypothesis whenever I get a score beyond this 209.84 with my predicted new population at 208. So let's make a line over here. So the predicted, let me just clarify that. The predicted mean here is as if I did a preliminary study. I got a sample mean from that as of 208. It's not my official study. I just did a quick little investigation, and that is still the best guess for the true population mean. if I now do my proper study with a large sample and everything is as big as I can make it to be as accurate as possible, I'm going to reject the null hypothesis if I get anything past 209.84. Now let's go back here and remember that if I reject the null hypothesis, that is the correct decision. When or what is the probability of me doing that? Well, I'm going to reject it whenever I get anything past 209.84. So this will be reject the null hypothesis, and that'll be done correctly. So let's see, can we calculate this area, looking it up in the table? Well, now for that, we're going to have to convert this 209 to its appropriate z-score in this distribution. So the z-score here will be 209.84 minus 208 over our our standard deviation of the comparison distribution, which in this case is a 6. And we will get, if my laptop wants to write the equal sign, we will get 0.31. Because it's really close, right? It's just past this mean. So it makes sense that it's super small, 0.31 only. So let's go and see what is this area for a z-score of 0.31. I have my table open over here. Percentage in the tail is what I'm looking for. Z-score 0.31, that sits over here. 37.38%. So that means here 37.38%. So that means the rest is, of course, 100% minus 37.38%, which will be 62.17%. So this is our type 2 error. The probability of correctly rejecting the null hypothesis, we'll call this the power. So power and type 2 error, they are just on opposite sides of this 100%. One is 100% minus the other. So this is, in this basic distribution, where a way to find the power and therefore also the type 2 error. When things get fancier as we progress, this isn't something we can do by hand, but for this simple normal distribution and simple situation, we can still manage to do that. So let's go through the steps here and see what we did. So we got the raw score cutoff point, 209.84. Then we said, let's move that up on the distribution of means for the population that receives this new treatment or the change or something has happened, population 1. In that distribution, because we now assume the research hypothesis is actually true, in that distribution, the 209.84 corresponds to a z-score of 0.31. And in that distribution, I have a little picture here as well. It's just a little small. For that one, We look it up in the table and we get a power of 37.38. That means that we correctly rejected the null hypothesis. So over here, this will be power. Correctly reject the null hypothesis when we should have. And then 100% minus the power will be, oops, wrong slide, will be 62.17, and that will be our type 2 error. So we'll do another example at the end, but I want to get this picture. Maybe this picture over here is a little better than my drawing, but it is exactly the same. So we start with the, let's say, the reference, the base comparison distribution. See where the cutoff is based on alpha. Then if the research hypothesis is true, I know it's blurry, then our true distribution is actually sitting around our predicted sample mean. The cutoff then is a different situation. We're much more likely potentially to reject when we should have. And we can calculate these two regions, power as well as type 2 error. It's a little bit prettier than my sketch, but I guess there's nothing wrong with mine. So start with the comparison distribution, follow it up, and calculate those regions. So if we look at the same situation, however, we have a much larger sample and therefore a much smaller variance. Then in my comparison distribution, without looking at all the detail, I still have an alpha of 5% rather, giving me a cutoff. If I follow that up, then the areas under the shifted distribution looks much different. The power is much bigger because it drops down so fast. There isn't much to catch it on the left to qualify as a type 2 error occurring. My chances of a type 2 error are much less because I'm much more likely to get that raw score or beyond. So but with a smaller variance, which can be achieved with a larger sample size, I am able to increase power and therefore decrease the probability of a type 2 error. Okay, so that's the first important note. But of course, there are other things worth mentioning when it comes to power. The effect size is very closely linked to power. That if the effect size goes up, the power goes up as well. Then, yes, effect size with the predicted difference between, which corresponds to the predicted difference between the population means. The effect size is just a standardized version of that. Of course, large difference, large effect size will imply that that top distribution shifted much further. We talked about the variance or standard deviation. If that's small, then we create this picture over here, not that picture. Can't remember which tabs I have open. This picture over here, which will make it much more likely to reject the null hypothesis correctly. And then, as we said, sample size, which is arguably the most important one here. Larger sample size has that that good effect of the standard deviation on the variance, that it decreases that, and that is one way, an easy way to increase the power. Of course, there's a balance between the significance level of alpha and power slash type 2 error. If I look at this and I increase my alpha to 10%, let's suppose it puts it over here, not 5%, but 10%. Then if I follow that line up, then I'll have a much bigger region, so a much higher power, and therefore a smaller type 2 error. But I increased the probability of making a type 1 error. So there is a balance between the two, but I can change one to improve the other. Oh, that's not the wrong slide. There we go. And of course, depending on if I have a one-tailed or a two-tailed test, I split the alpha up on both sides, and that can have an effect as well. The most important one here to think about is the sample size and what it means when I increase the sample size and its connection to the variance with this picture in mind. That was the time laptop. Change the picture. You're letting me down. Come on. There we go. With that picture in mind, there's a surefire way to increase the power and therefore decrease the probability of a type 2 error. Let's look at another example. Nope, I want to read the example first. There we go. I don't want to reveal too much of it, so we are in the bottom corner here. So if you remember the stress reduction example that we looked at, trying to see if whatever the treatment was reduces the stress ratings of people. So we have in our comparison distribution mean of 40, standard error of 2.24, and our predicted mean based on a preliminary sample probably is 34. So let's first visualize that. So I'll draw it with you. You can draw it as well. I'm going to make space here for the shifted sample and then focus for now on the standard. Whoopsie, that was supposed to be a straight line. On the comparison distribution. You know, I click the straight line tool. It doesn't want to be straight. There we go. So I guess I don't have to shift it that high, like so. So we'll just position this over here. I have to do it in little bits to try and make it nice and smooth for my bell curve. Over here, just sort of a standard shape. And that is, of course, centered at, I think it was 40. We can double check it. 40, yes. So now what we need to see is, well, what alpha do they want, first of all? We need to know what is our alpha. I probably, it's 1%. Alpha of 1%. Interesting. It's a left tail test because I'm trying to see if it reduces stress. So, hello, clicked on you. Okay. So we have 1%. Let's put it over here just for convenience. We don't have to make it super small. 1%. That means a z-score we can go look up. is negative 2.33. In case you're not sure, let's go and find that. We want 1% in the tail. 1%. That's going to be out there. Positive or negative 1%. So of course the table only lists the right side. We're edging closer to 1%. Another page over here. I guess this guy is a little closer. 2.33, but of course we're on the negative side. So that's where we get that. Okay, so that's 2.33. Then we want to convert that in this comparison distribution. What is the raw score? Well, it is the mean plus this z-score, negative 2.33, times the standard deviation of this distribution, which is 2.24. Calculate that, and we should get 34.78. Okay, so now let's see. Well, it's close, but our predicted new mean is over here at 34. So let's draw that distribution. Don't have a lot of space on the left here, but that should be okay. It's a little tighter than I want it to be. I want it to be the same width as this one, but it's supposed to be identical, the same. This one looks smaller. That's just coincidence. Same standard deviation, just a different position. So now I follow this up, give myself some space, and we got 34 point, what was it? 78. Whenever the laptop wants to agree, 78. So now we are going to reject the null hypothesis whenever we get a raw score to the left of this 34.78. And if it's shifted over here, this is going to be the correct decision to reject. So our power is going to sit over here, and our type 2 error, when we don't reject it, it's not extreme enough, but we actually should have, is going to sit over here. Regardless, we need this line that separates the two. That's going to be the z-score for this raw score of 34.78 in this new distribution, the shifted distribution, so to speak. Same standard error and everything. Calculate that, and we get 0.35. So where we are in our steps is we got the raw score from our comparison distribution. We then go to the distribution of means for the shifted situation, the change situation, because we assume that what if the research hypothesis is true and the population mean is actually different, centered at 34 in this case. We then get the z-score so that we can calculate, look up in our tables, either one of these areas, honestly. In this case, the area is going to be simpler if I focus on the type 2 error. So I'm looking at a z-score of 0.35. I think I'm going to have to go way up for that. Well, not way up. 0.35 sits over here. And I get in the tail 36.32. So that's going to be 36.32%. And therefore the power is just 100% minus that. I'll write that out. 36.32%. And what do we get? We get 63.68% for the power. And that is how we're going to calculate do our basic power calculations. When things get fancier, then it's not really something we can do by hand, but doing it in this simple situation, relatively simple still, gives us an idea of what does the type 2 error mean, whether I talk of it in terms of power or directly type 2 error. I'm thinking of this table, which I'm going to guess it's this tab. Ooh, that's the right guess. Where am I in this table? Type 1 error, I sort of choose by way of alpha. I can choose a more aggressive alpha if I want to lower the chance of making this mistake, this type of error, where I reject it, but I shouldn't have. But there's another error, type 2 error, where I should have rejected it, but I don't. Neither one of these should be very big. And there's a balance between them. I can choose one, but it affects the other one. And things like increasing the sample size, lowering the variance, and things like that can improve the type 2 error as well. All right, hopefully that made some sense to understand the issue with both of these errors, the connection between them, and how we can think about power and the type 2 error. Let me know if you have any questions. Until next time.